Hello everyone, welcome to the video number 6 of this video series on understanding FEA concepts with 1D example. My name is Vivek Varkal. In this video, we are going to see very important concepts of FEA. That is nothing but weighted residual technique and weak form. Okay. So before I jump into this weighted residual technique and weak form, let's recap quickly what we have learned. Okay, so we have earlier discussed about framework of FEM theory. Okay, and we derived a strong form first for a particular example, that is uh, rod subjected to axial force. Okay, and using strong form, in last lecture video number 5 we derived a analytical solution. Okay, so this is what we have got. This is the analytical solution, and this analytical solution for a simplified version. Okay, where we have taken q0 equal to 1, a equal to 1. Okay, and so this is a simplified form of strong form. Okay, u double dash plus 1 equal to 0, and this is a solution. Okay, so in this particular video we will see strong form to weak form. Okay, we will see how we will derive, how we will get to weak form from the strong form. Okay, so let's get started. Okay, so strong form, no, for a rod subjected to axial force, this is the one, AEU double dash plus Q0 equal to 0, subject to boundary conditions u at x equal to 0 equal to 0 and u dash at x equal to L equal to 0. Our length of the rod is L. Okay, this is a simplified where we are considering unit rod of the unit length of the rod, u dash plus 1 equal to 0. Okay, and subject to boundary condition u at x equal to 0 equal to 0 and u dash at x equal to 1 equal to 0. So these are two boundary conditions. Okay, and we have just seen what is the analytical solution. So in order to derive a weak form, let's get start with we'll start from the strong form. Okay, so this is our strong form. Okay, so before getting to weak form, we have to understand the weighted residual method. Okay, I mean this is a step by step process. First we will derive a weighted residual form, and then we will get weak form. So let's see the weighted residual form. Okay, okay. So weighted residual form, we will get weighted residual form with the two steps. Okay, the step one, and I will also try explain this in a physical significance. Okay, with physical significance. Okay, so step number one is nothing but uh, like we will assume solution. Okay, or we can also say trial function. So we'll assume a trial function. Let's say it is a u. Okay, we are trying to solve u, right? So let's say it is a u. Okay, and there are two things. Okay, uh, if this u, whatever we have assumed this solution, if it is an exact solution, it will satisfy the strong form, right? So in this strong form, if we substitute our solution, assume solution, we'll get 0, right? So this will satisfy the strong form. However, since this is a assumed solution or trial function, okay, our solution is a not exact solution. because it is a trial function. Okay, so when we substitute our solution in strong form, okay, it is not going to be a zero. Okay, so what we get some residual or error, right? We can say we get some residual or error, and we denote it as rd of x. Okay, so like this is our rod length. Okay, and we get a error, okay, with respect to the x. Okay, so this is a step one, and step two is once we get a residual, we say that the residual rd of x is minimized over the entire domain, over the entire domain in weighted sense. So this is highlighting a word weighted sense. Okay, so let's try to understand. Let's no say let's take this our length. Okay, 0 to 0 to L. Okay, this is x. Okay, so this is our exact solution which is unknown. Okay, now we have assumed a trial function. Okay, so let's take some uh, trial function we have assumed. Let's take something like this. I'll take it different color. Okay, let's take this is our assumed function or assumed solution. Okay, so we'll get some residual, right, or error. So we get rd with respect to x. There is an error along the axis of along the length of the rod. Okay, now what we are saying, this residual, okay, we cannot make residual zero at all the locations at or I'll say residual zero over the entire domain, right? Entire domain at each point. Okay, so what we are saying, we'll try to minimize over the entire domain in a weighted sense. What does it mean? Okay, so if I take weighted sense means we'll multiply this error rdx, okay, with some weighting function. Okay, weighting function is nothing but it is a contribution, or we can say it is a weightage at each points, okay, or and over the domain with respect to x. So we'll take some weighting function and multiply it with error, and we will say uh, this weight average sense we will try to minimize. So when we take integral, okay, we'll make it as we will make it zero in a average sense. Okay, that means this residual, residual at this location will multiply with the weightage. Okay, we'll sum it up, we'll multiply all the residuals or errors with a weighting function, and at each point we'll sum it up, or we'll take integral, and that complete integral or summation of no this error into weighting function will make it a zero. Okay, we'll try to make it zero. Hope it makes sense. Okay, and therefore this is what we get. Okay, and this is nothing but a weighted residual technique, so we'll just apply it to our problem. Okay, so our residual with respect to x we'll put, which is nothing but ae u double dash plus q0. This is our residual into w. So I will just keep it only w. Okay, w of x. So this is our weighted residual form of strong form. Okay. So once we get a weighted residual form, we'll just derive the weak form. Okay. So now we are moving to weak form now. Weak form. So we'll continue this weighted residual form to derive a weak form. Okay. So this is our weighted residual form. So what I'll do, 0 to L. I'll just expand. I'll just do some mathematical operations on this. U double dash into W dx. So I'll not write W of x. W is a function of x, so I'll not write it just to make it easy to visualize this equation. Okay, so I will say A U double dash W dx, okay, plus Q0 W dx equal to 0. Okay. So let's further expand. Okay. Now here we will do something called integration by parts. So there is a standard formula for integration by parts, which looks something like this. Okay. 0 to L u v dash dx is equal to uv minus 0 to L u dash v dx. Okay, so this is a very standard formula. You can search online, and you can try to understand this formula with proof. Okay, so we'll now we are not doing a mathematics lecture, so we'll just take this formula for now. Okay, now what I'll do, I'll put u is equal to, okay, u I will take it as a w. Okay, and v I will say, sorry, this u is there, v dash I will say it is a u double dash. Okay, so I'll just put it here, 0 to L uh, w to a u double dash dx is equal to, okay, w v is nothing but the this one order less than this v dash. Okay, so it should be a u dash, okay, one order less, 0 to L minus u dash is u is equal to w, so w dash. Okay, and v is again one order less of this, so a u dash dx. Okay, so we have got this one. Okay, so what I'll do, I have done nothing. Okay, I'll just apply the integration by parts for this one. Okay, and I will substitute this one in this one first term of our this equation. Okay, so a u double dash w dx, here we have, we'll just substitute this here. Okay, so if I do that, So w, I'll just put w of x. So I'll put sometimes w, sometimes wx. So you just understand, okay, it is a function of x. Wx a u dash, okay, 0 to L, this one minus this minus 0 to L w dash a u dash dx plus this term plus 0 to L q0 w dx equal to 0. Okay. So this we can write something a I'll just put this limit here. So ae u dash at x equal to L. Okay. This is nothing but uh, p. Okay, we'll denote it as a p. Okay, which is at x equal to L. So this is nothing but our axial force. Axial force at x equal to L. Okay, or we in another term we can say this is an internal force, right? Because it is coming from u dash, so it is internal force. Okay, at boundaries, and we'll put this also limit 0. So I'll say a u dash x equal to 0 is equal to p of x equal to 0, or we'll denote it as a p0, and this is a pl. Okay, so what I'll get this first term I'll write it as w at wl pl minus w0 p0 p0. Okay, this one, and this I'll write it as it is minus 0 to L a, a u dash w dash dx plus integration 0 to L w q0 dx. Okay, so this is our weak form is equal to 0. Okay, okay. So just we'll try to understand these terms. So these two terms we have already explained. Okay, these are nothing but internal forces. Okay, at boundaries, at boundaries due to boundary conditions. Okay, this term is simply, we know what is this. This is an internal force. Okay, internal force within the domain. So we'll say this is internal force, or we can say internal contribution. Okay, and this is q0, we know it is a external force. Okay, so this is a external force or external contribution. Okay, so we know q0 is nothing but we have defined it as a uniform varying load, uniformly varying load. Okay, which is nothing but Newton per mm. Okay, so remember this is our weak form. Okay, weak form. Okay, this is also called a variational form. This weak form is also called variational form. So let's see what this weak form means. Okay, so if you remember in our strong form, okay, which is AEU double dash, okay, AEU double dash plus Q0 equal to 0. Okay, in our strong form we had d square u by dx square. Okay, whereas in our weak form we have only u dash. Okay, so weak form has u dash or du by dx. Okay, so what okay, in strong form, okay, if we wanted a solution, okay, ux choice has to be quadratic, right? Okay, because it is a double differentiation. So our u of x choice or selection which we make, it has to be quadratic. Okay, whereas since this is a on in weak form we have only once differentiation, only one derivative. Okay, the selection of ux, okay, is allowed to be linear also. Okay, so our trial or assume function, as we initially we have mentioned uh, here, okay, assume a function or solution, let's say u, it can be even, it need not be a quadratic, it can be linear function also. Okay, other observation in this weak form, okay, this one, wl pl w0 p0. Okay, that means pl and p0. So this is, let's say this is a first observation, and second observation is force boundary conditions. Okay, or force boundary conditions are also called natural boundary conditions, whereas displacement boundary conditions are called essential boundary conditions. So these natural boundary conditions, okay, uh, p0 and pl, they are embedded into weighted residual form itself. Okay, so they are inbuilt into the function or our weighted residual form. Okay, pl and p0. So that is another observation, uh, and that means our assumed solution or a trial function need to satisfy only essential boundary conditions, because natural boundary conditions are inbuilt, okay, embedded into weak form itself. So what are essential boundary conditions? That u at x equal to 0 equal to 0, right? This we have said, subject to boundary conditions u of 0 equal to 0. So this is our essential boundary conditions. Essentials, why essentials? Because in order to solve the problem, this is the essential boundary condition. Okay, we have seen this in earlier videos. Okay, there must be a constraint in order to solve the problem, right? Okay, and third observation, uh, okay, is that continuity demand on u of x, it's reduced by one order. Okay, because we have reduced from u double x u double dash of x to u dash of x, right? So continued demand is reduced, and that is the reason it is called weak form. Okay, so these are three important observations. One is The UX choice of UX can be linear function also. Okay, we can assume u of x as a linear function. Second observation, this is very important, we will see in upcoming lectures. Okay, why we took a linear function, it is because of this one. Okay, second observation is that force boundary conditions are embedded into weak form itself. Okay, so I'll say not a weighted residual but weak form itself. Okay, and continuity demand is reduced. Okay, so this is our weak form. Okay, and I will just simplify it further. Okay, so we had no boundary conditions. Our boundary conditions were u of 0 equal to 0. Okay, u dash of l equal to 0. Okay, and we will also put condition that w of 0 equal to 0. What is that? So what we'll do, you remember the weighting functions, we multiplied it with weighting function right here. Here we assume the solution and multiplied the residual with weighting function. Okay, so let's see what is a weighting function. So okay, so weightage function or weighting function can be arbitrary function. Okay, it can be anything, right? Anyways, because why arbitrary? Because we are going to minimize the residual in weighted sense. Okay, so whatever it can be, after all we are going to reduce the residual in weighted sense. So it is arbitrary function, it cannot be a zero, so it is a non-zero function. So that is very obvious, right? It is a non-zero function, and since it is a function of x, it should be integrable function. Okay, why integrate? Because we have said we'll take integral. Sorry, here we said we'll take no, integral of rated residual into weightage function is equal to 0, so it should be a weight integrable function. Okay, so these are three properties of weighting function. Okay, so we what we'll do, we'll choose v w of x such that w of 0 equal to 0. Okay, and when we put w of 0 equal to 0, okay, our weak form, this will become 0. This PL, as you know, it is a, it is already there, a u dash x equal to 0. Okay, and this is our boundary condition. Yeah, right, u uh, u dash u dash of l equal to 0, so this is also 0. Okay, so this is further simplified, so only these two terms are available now. So I will rewrite this form: 0 to l a u dash w dx is equal to 0 to l w q0 dx. Okay, so this is our weak form. Okay, this is our weak form. Okay, so let's summarize. Okay, let's summarize this lecture. Okay, uh, we had a strong form, then we used weighted residual technique and we got a weighted residual form. Okay, from weighted residual form we got weak or variational form. So, so our strong form is A U double dash plus Q0 equal to 0. Okay. Subject to boundary conditions of U at x equal to 0 equal to 0. We are talking this on rod, right? Rod subjected to axial force. So this particular example we are talking U dash of L equal to 0, 0 less than or equal to x less than or equal to L. Okay. Weak form is simple, right? This is our assumed solution. So A U double dash plus Q0 and assumed solution B. This is assumed solution, that means this is a residual. Okay, this we multiply with our weighting function and take integral, and then we say we'll minimize. So this is our weighted residual form. Here also we'll say u0 equal to 0 and u dash at L equal to 0. And what is our weak form? Weak form is 0 to L w dash a u dash dx is equal to 0 to L w q0 dx. We can see here one order is reduced. Okay, u double dash to u dash. Okay, subject to boundary conditions of u at x equal to 0, u dash at L equal to 0. Okay, and another also we have said we'll choose weighting function such that w of 0 equal to 0. Okay, so we now we have three conditions. Okay, so this is a summary, and if you remember, always try to, you know, we always try to get along with our original or full strong form. We also try to simplify also, right? So if here u double dash q0 divided by a is equal to 0, we have also try to get analytical solution for this simplified form u double dash plus 1 equal to 0. Okay, simply let's write this for a simplified. Okay, simplified means 0 less than equal to x unit rod length, and q0 and a is equal to 1. Okay, so our strong form is u double dash plus 1 equal to 0, that we are well known to that u of 0 equal to 0, u dash at x equal to 1 equal to 0, and unit rod length. And what is a weighted residual form? As we said, we'll assume trial function, and since it's a trial function, we get the residual. So this is our residual. We'll multiply it with our weighting function, and try to minimize it in an average sense over the domain 0 to L 0. Okay. So this expression you remember in that way what I have just explained to you. Okay, since u is a assumed or trial function, when we substitute u in our strong form, we will not get 0. Okay, so this is a residual we get. Okay, when we so what we do, the residual we will multiply it with weight function and minimize it over the domain in average sense. Okay, so this is the meaning of this particular equation. So we'll say subject to u0 equal to 0 and u dash at 1 equal to 0. Okay, and what will be the weak form for this? Okay, it is a very simple 0 to 1. Okay, sorry, this should be 1. Okay, so 0 to 1 w dash u dash dx is equal to 0 to 1 q0 dx, right? U at 0 0, u dash 1 equal to 0, and w0 equal to 0. Okay. So this is what we learned in this particular video, and in next lecture we will continue from weak form to approximate form. Okay, so with that, this is the end of this lecture. Thank you very much, guys.